Hello everyone, my name is Monowar and welcome to my final presentation of CSE424 pattern recognition. Today I am going to be talking about a project I am really passionate about titled Biomedical Syntactic Pattern Recognition, clustering DNA sequences. Before I begin, I want to take a moment to thank you my course instructor Mohammad Sabir Hussain sir for his guidance and support throughout the semester. For this project, I decided to take a completely different approach to biology. Uh, Instead of looking at DNA as just chemical data, I treated it exactly like software code. Today I am going to walk you through exactly how I did that, why Stanford deep learning failed, and how I achieved almost 84% accuracy using linguistic pattern recognition. Let's start by looking at the core problem. Traditionally, when machine learning is applied to DNA, researchers rely heavily on numerical averages. A common one is GC content, literally just counting the percentage of guanine and cytosine. But I argue that this approach is deeply flawed. Why? Because it completely discards the structural sequences and the syntactic meaning of the code. Think about it like this: if you want to understand a novel, you don't just count how many times the letter A or the letter B appeared on the page. You have to actually read the sentences. That is the what normal ML does. It ignores the sentences. My solution is to treat DNA as a linguistic software system. If DNA is the source code of life, it has a grammar. On the slide, you can see the top-tier hierarchical genomic logic tree I built. By utilizing grammar-based logic and syntactic pattern recognition, my goal was to decode genetic function much more effectively and far cheaper than traditional biological alignment tools. Moving to my exploratory data analysis. For my dataset, I pulled over 8,000 raw genomic coding sequences, but I did not just restrict this to humans. I include sequences from chimpanzee and dogs as well. This was a super important decision because I needed to prove that the grammar rules apply across completely different evolutionary branch, not just in our own species. I evaluated seven distinct biological gene families like RNA, tRNA, and pseudogenous. However, when I mapped the initial data distribution, I found some severe class imbalances. Some of the minor evolutionary fragments were tiny. For example, the snRNA class only had 7 samples in the test set. If you feed a class of 7 samples to a machine learning model, it does not learn, it just memorizes. It will start hallucinating results. So, to fix this, I made the strict decision to filter out any minority noises, specifically classes with fewer than 10 samples. I had to do this for to guarantee a robust baseline for my feature extraction. Before I started coding, I need to make sure my theory was backed by literature. I found three fundamental concepts. First, Logan et al. Demonstrated that edit distance, which basically measures how many edits it takes to run one string of text like another, captures special sequences syntax significantly better than aggregate math like GC content. Second, Lodi et al. Proved through their work on string kernels that comparing raw string subsequences is a highly effective way to categorize the text. And finally, Ng incredible DNA2 VC research proved that if you chop DNA into overlapping pieces called kmers, you can treat them exactly like linguistic token in natural language processing like NLP, and they will yield consistent, mappable biological meaning. With the NLP foundation set, I had to figure out which algorithm to actually use. When you transform DNA into text feature using TF-IDF, it creates highly sparse matrices, basically thousands of columns of zeros. Hocketer showed the NLP techniques are robust for kind of biological data, but the real breakthrough from the reading Greenstein et al. They proved that gradient boosting consistently outperformed deep neural networks on tabular and high-dimensional sparse matrices. Deep learning just get lost in all empty spaces. Because of this, my champion architecture choice was LightGBM. LightGBM used an exclusive feature bounding and leafwise growth strategy, make it mathematically ideal for navigating sparse genomic spaces without overfitting. This brings us to my methodology. I designed a rigorous 23-phase pipeline. I did not want to just throw data at a model and hope it worked. I wanted mathematical proof first. As you can see, the pipeline is divided into two halves. Phase 1 had to unsupervised focus on establishing mathematical proof that this structure actually exists before any human levels are applied. Once I had that proof, phase 2 had a supervised focus scaling the predictive accuracy across multiple machine learning architecture to find the absolute best one. So let's look at the phase 1. This was a huge milestone for the project. The algorithm computed a massive n-by-n Lebesgue edit distance matrix, and then verified the structural clustering against the ground truth biological label using the adjust rand index, or as known as ARI. If you look at the UMAP projection on the right side of the screen, this is the visual proof. The sequence naturally group themselves into isolated genomic islands based purely on syntax. The predicted clusters reached an ARI of 0.3484. I even ran a permutation test and the p-value came back at less than 0.0010. This proved conclusively that the syntactic structure is mathematically real and it's not just random luck. Since the structure was real, I moved to feature engineering. How do we translate biological string into machine learning feature? We borrow from natural language processing. For tokenization, I decompose the raw DNA string into overlapping 4 nucleotide units, known as kmers. So, a sequence like ATGC GT becomes ATGC, and then TGCG. We are basically creating a biological dictionary. Then I apply TF-IDF weighting. TF-IDF is amazing, like here, because it punishes common background DNA and heavily reward the unique signatures that actually matters. These generate a massive sparse 5000 dimensional matrix. This chart on the right display top 20 discriminative formers motifs that the algorithm found in this matrix. Then come to the super leaderboard. I tested 16 different model and we ran into a massive Bottleneck. Traditional model like decision tree failed terribly at 31%. But surprisingly, sequential deep learning also failed. My hybrid CNN LSTM plateaued at 68.7%. When I dug into the error, I found out first, neural network struggling map weight across 5,000 dimensions of mostly zeros. Secondly, they suffer massive false positive because pseudogenes. Pseudogenes are basically dead. Evolutionary leftover, they don't function, but their Kmart syntax looks amazing, almost exactly like real genus, which completely fooled the nature networks. But our champion model, LightGBM, did not get fooled. It achieved a peak accuracy of 83.72%. LightGBM won because its leafwise tree growth perfectly navigate and empty spaces in the TF-IDF matrices. I ignored the uniform noise and found the syntax in the sparse the classes. To be absolutely certain, LightGBM was not just getting lucky. I plotted a multi-class AOC ROC curve for final validation. The one this rest performed was incredibly stable. We saw a perfect one for RNA and the near perfect 0.998 for tRNA. But here is the most important part of the trickiest class, those dead pseudo genes that ruin the deep learning models. LightGBM achieved highly separable 0.947. It successfully learned the mini syntax differences that separate functional genes from evolutionary noise. To conclude the research, biological function is effectively and efficiently decoded through the syntactic grammar rather than aggregate numerics. The methodology successfully scaled from unsupervised ARI validation all the way to an 83%, almost 84% classification accuracy using the gradient boosting. It proves tree-based model easily beat deep learning in specific domain. For future reason, there is a lot more to explore. I want to expand the linguistic sliding window from 8 marks to 8 marks to capture wider context. I also plan to integrate advanced context-heavy attention to much to mechanism like DNA birth, assuming I can get access the necessary GPU compute power to see if transformers can capture even deeper long-range biological sequences. Thank you very much for your time and attention to my final presentation. Here is the first page of my academic references covering the foundation pattern recognition and NLP string classification. And here is the second page of references highlighted light GBM architecture and optimized Levstein distance matrices. Thank you again.